I'm going to talk to you mostly about projections of global mean sea level change in the AR5, but I'd also like to say a few words about climate change in the AR5, because that, of course, is the context. So the AR5 repeated the statement that was made in the AR4, which is an important statement: the warming of the climate system is unequivocal. This, of course, is based principally on the first thing that comes to mind is the global mean temperature record, but also there are other elements of the climate system that support this conclusion, in particular ocean warming, as Annie has showed us, reduction of ice on land, as Jonathan has shown us. And the global mean temperature time series, updated to 2012, is shown here. If you fit a trend from the latter part of the 19th century to now, and use that to work out how much the temperature has gone up, the answer is about 0.85 degrees. The lower graph shows you decadal means, which of course gets rid of a lot of the variability and points to the striking conclusion that each of the last 3 decades, that's calendar decades, has been successively warmer at the Earth's surface than any of the preceding decades. And that is quite clear, I think. So, now we know, of course, on physical grounds that we would expect an increase in greenhouse gases in the atmosphere to warm up the Earth system, and we expect that CO2 concentration from calculations has made the largest contribution to that radiative forcing. We know for sure that it has been going up in the instrumental period since the 1950s, during which it's been directly measured, and we know from ice cores that it has been going up on longer timescales and now stands at a level that hasn't been reached for at least 800,000 years. That is the length of the ice core records. Since the Industrial Revolution, we can explain the amount by which CO2 has gone up in the atmosphere, and it's about 2/3 due to fossil fuel combustion, 1/3 due to land use change. But now it's about 10 to 1 in favour of fossil fuel combustion at the present time. And as a result of that, by putting the CO2 concentration and the concentrations of other greenhouse gases and anthropogenic agents into climate models, it is possible to reach the conclusion that it is extremely likely that human influence has been the dominant cause of observed warming since the mid-20th century. And that is based on comparisons such as this one. Wrong end, is it? What, how do you use this? I forgot my name. Is that button? This button? Oh, got it. Right, thanks. Where the simulated model mean global temperature time series, which is a pink, well, this is the model range, the pink band, agrees very well with the observed change. Whereas if you omit the anthropogenic forcings and you just have natural forcings, that is principally volcanic eruptions and solar irradiance changes, you don't get that recent increasing trend. So you're familiar with all those conclusions. Now, a global mean sea level rise is also sometimes cited as evidence of global warming. And to some extent it is, but it's not quite as simple as that. On the long term, of course, geological timescales, global mean sea level rise is caused by change in the volume of the ocean basin, amongst other effects. But if we consider only climate change, timescales, centuries or millennia, what we are concerned about with global mean sea level rise is a change in the volume of water in the ocean. And that is caused by change in the density of the ocean water, as has been discussed by Annie, who showed the budget previously, which is nearly entirely thermal expansion due to warming, and changes in the mass of the ocean due to water going into the ocean, which is currently in the form of mass or water on land. I would like to make an advertisement for the new word, barystatic in red there, which may or may not catch on, but this word is proposed to mean the contribution that comes from adding mass to the ocean. The change in global mean sea level comes from adding mass to the ocean. Of course, you could call this the mass term, but in some contexts that's confusing, because the mass term could mean the change in local sea level caused by the modification to the geoid. Another word that has been used for this is eustatic, but that's confusing too, because the original meaning of eustatic is global mean sea level change, so that means it has 2 meanings which are not consistent. And for that reason, the last 3 assessment reports have all recommended the word eustatic should not be used. So this word barystatic is proposed as a possible alternative if you would like to use it. It's a newly invented word that hasn't previously been used except in Star Trek, where it means something different. Now, I'd like to talk about the contributions to global mean sea level rise and how we reach our assessment of confidence in the projections that we make in the AR5. we've got high confidence in the projections of thermal expansion. And this is because we now have good observationally based estimates of thermal expansion, as Annie has showed us. That is shown here as the blue shaded band and the solid blue line, which is the mean in the middle. So this is a calculation from observed ocean 3D temperature sampling. And this record has improved a lot since the AR4 because of the identification and correction of some observational errors. So we've got more confidence in that than we used to have. Then we also have the consistency of historical simulations with GCMs with the observations. So these grey lines here are individual GCMs and the solid black line is the mean of GCMs. And you can see there's a very good agreement between the GCM ensemble mean and the historical record. Because the GCMs have been forced with anthropogenic and natural forcings, this gives us evidence that the warming of the ocean is at least partly anthropogenic. But there is also a natural influence, which can be seen from the dips in the black lines, and that's when a volcano erupts that temporarily cools the Earth system. So we expect to see that signature there as well, but clearly it's not dominant. There's more variability in the observed record than there is in the black line, because the black line is a mean over many GCMs, so internal variability such as ENSO effects tend to be averaged out. And thirdly, we have overall a better understanding of the Earth energy budget, which means that we can demonstrate a consistency between our estimates of radiative forcing, climate sensitivity, and the amount of heat that is observed to being stored in the Earth system. And because this kind of this budget is well closed within uncertainties, that leads us to believe we have some idea about what's going on. So these strands of evidence mean that we have high confidence in our ability to project thermal expansion using GCM projections of ocean temperature change. We've got medium confidence in projections of glacier mass loss. Again, we've got records of glacier mass loss. Jonathan has talked about this already, going back several decades. And there is a consistency of historical simulations with observations for this too. So this figure actually comes from chapter 4. And the important point is that the purple line of Marzayan et al. Is actually a model, whereas the other ones are glaciological measurements, based on glaciological measurements, showing an agreement there. And this gives us confidence because the model of Ben Marzayan is the same kind of model as we use to make projections. And those models have a process founded on process-based understanding of what are the influences on glacier mass balance, although they are simplified for dealing with the total ensemble of the world's glaciers. So these are sources of confidence, but we assess our confidence only as medium because, as Jonathan has mentioned, the set of well-observed glaciers on which the observations are based and the models are calibrated is a very small fraction of the total number of glaciers in the world. So because a sort of extrapolation is involved, we can't be entirely happy about that. And then going to ice sheets, I have a figure here which you've already seen twice before. We all have a different thing to say about it. So we know, thinking first about Greenland, from the comparison of different methods of measurement of the change in mass of the Greenland ice sheet, that about half the increased mass loss is due to increased surface melting over recent years, meaning the other half must be coming from increased ice discharge into the ocean. Now, the modelling of surface melting is done with high-resolution climate models, typically, of the same kind as we use to make projections. Therefore, the agreement of observations with models for the past gives us confidence in our projections of increasing Greenland surface mass loss in the future, which is an obvious consequence of warming that will occur in Greenland, leading to greater melting exceeding the expected increase in precipitation. We also expect that Greenland will warm more than the global average. Whereas for Antarctica, we also have RCMs that can give us surface mass balance, which in the case of Antarctica is essentially precipitation, because that is snowfall, because there is practically no melting. But as Jonathan has said, these models, when considering the past, don't show a trend in increasing Antarctic snow accumulation, and therefore the increasing rate of mass loss in the Antarctic must be entirely due to increased outflow, not due to melting, because there is not any. Now, all GCMs, global GCMs, project for the future that Antarctica will warm, and consistent with that, there will be more precipitation and therefore more snowfall. But these trends have not been observed so far. So, despite the fact that we have good physical reasons for expecting that to happen, because it's not observed, we have only medium confidence in that projection. So those are for the surface mass balance components, and then for both ice sheets we also have to deal with the more difficult question of what will happen to the ice sheet outflow in the future. And because we don't have complete deterministic process-based models of the ice sheets, we based this assessment on a range of different kinds of evidence in the literature. They are process-based models for parts of the ice sheet, statistical extrapolation of recent trends, and some expert judgment. And putting all these together, we arrive at likely ranges for the contributions to increasing outflow from the ice sheets with medium confidence for the 21st century. So those are the components. The other source of confidence comes from whether or not we can explain the total observed sea level rise. As has already been said, since in the recent Holocene, the last couple of thousand years, the rate of sea level rise inferred from proxy data, such as particularly salt marsh data, shown here as the light purple, was small, of the order of maybe 1 or 2 tenths of a millimetre per year. But since the middle of the 19th century, the rate of sea level rise, or the late 19th century, sometime in the 19th century, the rate of sea level rise has been substantially larger. And we know from tide gauges the rate during 1901 to 1990 was about 1.5 millimetres a year. In 2002, Walter Monk wrote a paper called 20th Century Sea Level, an Enigma, in which he complains that the historic rate of sea level rise started too early, was too linear, and was too large. And this is a kind of challenge to us to explain this, and we have made progress on these questions in the last few years. This is a figure from a paper of which I wrote with many collaborators who are experts in the various parts of the budget, putting together what we now know about how we could explain sea level. This is just one possible example. There are many possible permutations of data sets. The black line here is the observed, the thick black line is the observed global mean reconstruction of sea level rise by Church and White. And the red line, the thick red line that practically overlies it, is a sum of estimated contributions. And you can see very good agreement there, leading us to think that in fact we can largely explain 20th century sea level rise now. It is not such an enigma as it was. And the dominant contributions are the light red line, thermal expansion, and the light black line, glaciers. And both of those estimates are larger than previously, and that's why the budget is better closed than it used to be. It's notable, I think, that the black line, the glacier contribution, is a fairly straight line. That is, the rate of mass loss by glaciers didn't increase very strongly during the 20th century. And there are two possible reasons for this that have been put forward. One is that in the early part of the 20th century, there was a warming in high northern latitudes, especially in the Arctic and in Greenland, and glaciers therefore in those regions lost mass quite rapidly. And the other reason is a general observation that when glaciers lose mass, the parts they lose are, of course, the low altitude sensitive parts, which means their sensitivity to future temperature change is reduced. So you have a kind of compensation between the fact that the warmer it gets, the more the glaciers should be losing mass per square metre, but the fewer square metres they have, especially sensitive ones, left to lose. And that counteracts the acceleration, and you end up with a straighter line. And then the rest of the budget can be closed, can be explained by mass loss from the Greenland ice sheet, especially during the earlier 20th century, when models suggest and data suggests that because of the warm period, the ice sheet may have lost mass at a greater rate. And the Antarctic ice sheet, which is shown here as a straight line, that's this dark blue one here, effectively just to close the budget. But to close the budget requires only, in this case, 0.1 millimetres a year, which is consistent with the long-term adjustment of the Antarctic ice sheet to the end of the last glacial, as Jonathan mentioned, and is not inconsistent with the proxy evidence of sea level change over the last couple of thousand years, which permits a small contribution like that. There's also a net contribution from land water storage, which is these two lines. The purple solid one is the groundwater mining term, which has increased markedly recently, and the dashed purple line is a negative term due to reservoir impoundment. And these are, and their net effect is rather small during the 20th century. And then when we turn to the recent years, Annie has already discussed this budget, so I needn't do so. we find that there is a greater rate of sea level rise, and model-based estimates suggest that this greater rate is at least partly forced because of the greater thermal expansion and glacier mass loss, but there is also the contribution from the ice sheets, which has increased, and that may not be anthropogenically forced. That might be internal variability. So now then, turning to the future. In the AR5, a new set of scenarios were adopted for considering possible futures, and these are called representative concentration pathways, RCPs. So the difference between these and the preceding SRES scenarios that we used in the AR4 and the TAR is that these are principally concentration time series, not emissions time series. So that the job is being addressed backwards with respect to previous assessments. Carbon cycle models are still used, but they are used to work out what are the emissions which would be needed to follow one of these prescribed concentration pathways. And the concentration pathways themselves are input to climate models. So this graph here compares the relative forcing of the RCPs, the solid lines, with the SRES scenarios that we used in the AR4. So you see that the scenario of greatest concentration increase, RCP 8.5, is comparable with scenario SRES A2 of the AR4. The lowest one, RCP 2.6, sorry, this one, RCP 2.6, is a much lower scenario than the lowest scenario considered in SRES, that is SRES B1 here. So this scenario actually has a reduction in radiative forcing by the end of the 21st century. The reason for this is because the RCPs, unlike the SRES scenarios, do explicitly allow for the possibility of policy measures to mitigate climate change, whereas the SRES scenarios were all non-mitigation scenarios. So RCP 2.6 in particular does imply severe measures taken to limit CO2 emissions, and in fact to achieve this pathway requires negative emissions in most models in the latter part of this century, that is taking CO2 out of the atmosphere. Under these scenarios, when they are applied to GCMs, we conclude that continued emissions of greenhouse gases will cause further warming and changes in all components of the climate system. That, of course, is a statement of very high confidence. And the GCM results for global mean temperature change are shown here. The coloured bands are the 5 to 95% range of GCMs, and the bars at the right are the likely ranges for 2081 to 2100. And the likely ranges are in fact the 5 to 95% range of GCMs, but they are interpreted as likely because we don't include all possible uncertainties. And they are not very likely ranges, but likely ranges, meaning the judgment is that the true answer has a 2/3 roughly probability of lying within these bars for a given scenario. So you see there's a large difference between what you get with RCP 8.5 by the end of the century and what you get with RCP 2.6. But limiting climate change, as suggested by RCP 2.6, will require substantial and sustained reduction of greenhouse gas emissions. In the upper two scenarios, RCP 6.0 and RCP 8.5, global mean surface temperature change by the end of this century is likely to be more than 2 degrees above pre-industrial. And the reason for drawing attention to that is because 2 degrees is a policy target. Meaning that if we want to have a good chance of reaching that policy target, we cannot follow RCP 6.0 or RCP 8.5. Okay, oh yes, this is important too. So this is a new feature of the AR5, which I think got quite a lot of press attention. It turns out if you plot the cumulative CO2 emissions, which is on the x-axis, against the global mean temperature change that it produces, you get a well-defined scenario-independent relation. You see all the RCPs overlying one another here. And it's also a fairly straight line. This black line here is a different straight line for the 1% CO2 idealised scenario. So not quite the same, but not very different. So this graph gives you the impression that the global warming you get, is essentially linearly proportional to the cumulative CO2 emissions. And that's a useful policy tool because it means you can translate the temperature target you would like into the CO2 that you're allowed. As the global mean surface temperature continues to rise, of course the global ocean will continue to warm. Heat will penetrate from the surface into the deep ocean. As you've shown here, this is a model mean by the end of the 21st century in RCP 8.5, and you can see the warming is biggest at the surface and penetrates downwards. And the stippling shows where the models agree strongly, that is, the change, the ensemble mean temperature change is at least twice as big as the internal variability. And this ocean temperature change, of course, means that there will be more thermal expansion. There are consequences for ocean circulation. For instance, the Atlantic meridional overturning circulation is likely to decline during the 21st century, the same result as was shown by previous generations of models. Warming and precipitation change will not be uniform. These figures show patterns very similar to those that you would see in the AR4 and previous multi-model assessments. So the upper panel compares RCP 2.6 and RCP 8.5 surface temperature change by the end of the 21st century. And you can see that clearly the warming is more intense in RCP 8.5, but the geographical patterns are quite similar, and they show the familiar features of enhanced warming at high northern latitudes and greater warming over land than over sea, for both of which there are good physical reasons. The lower panel shows change in average precipitation. Again, the pattern is similar but greater, more intense in RCP 8.5. And a general way of characterising these patterns is that areas with large precipitation receive more precipitation, and areas which are largely dry become drier. So in general, it's an intensification of the existing hydrological cycle. The models generally suggest, those models which have a reasonably good simulation of Arctic sea ice, and that by the mid-century it's likely that the Arctic Ocean will be ice-free in September. Of course, the ice still regrows in the winter in RCP 8.5, but there is only medium confidence in that statement owing to the deficiencies in simulation of the large spread of results that models get. So because temperature goes up, and that's a more important effect for surface mass balance than the increase in snowfall, we expect glaciers to continue to lose mass. And here we show, in the coloured lines, projections by 3 different glacier mass balance models, surface mass balance models, with various AR5 ANGCM results, and the black lines that are on the outside are our assessed likely range for glacier mass change during the 21st century. And you see that a large proportion of the glacier mass is expected to be lost. In RCP 8.5 in particular, up to 85% of the current glacier mass might be lost by the end of this century. And these individual lines are also, while they do show some curvature, are relatively straight, some straighter than others, and that is for the same reason as I mentioned earlier, that the glaciers are losing mass, and this restrains their rate of mass loss despite the fact the temperature is going up. Okay, so in the beginning I went through the reasons for our confidence, that is the agreement of the models of individual components with observations of those components, and the agreement of the observed total, our ability to explain the observed total in terms of those contributions. So because of these two developments, our confidence in projections of global mean sea level rise has increased since the AR4. The projections of global mean sea level rise are larger than the AR4, and I'll show you this in detail later on, after accounting for scenario differences. And this is primarily because of improved modelling of land ice contributions. We are able to include in the AR5, unlike in the AR4, a quantitative assessment of the contribution that will come from the changes in ice sheet outflow on rapid timescales, whereby rapid is meant decades. That is not the slow response of the ice sheets, which takes thousands of years to changes in surface mass balance. And these are the effects that have been responsible for the increased rate of outflow in the recent decades. But the current state of knowledge is not sufficient for us to assess the dependence of these terms upon the scenario in our judgment. Because not all the terms have high confidence, in the end we have only medium confidence in our likely ranges, but it is a big step forward that we are able in the AR5, as a result of this improved confidence, to give likely ranges for sea level. In all the previous IPCC assessment reports, the sea level projections were described simply as the results of models. No statement was made about whether they were likely to be right. And effectively we are now making such a statement by asserting that we think the true answer is likely to lie in these ranges for a given scenario. Under all the RCPs, it is very likely that the rate of global mean sea level rise, on average, during the 21st century will exceed that which was observed during 1971 to 2010. And you can see that graphically here, because here we have joined together the projections, which are the bands at the end, these things at the end, with the observed rate of rise from tide gauges, which are these coloured lines here. And here are the, focusing on the 21st century, here are the projections for the RCPs. So we have in the bands here the likely ranges for RCP 2.6 and RCP 8.5. And over here in the bars, the mean for the last 20 years of this century for all of the 4 RCPs. You see that up to the middle of this century, the scenarios are not very much different, because a large part of what's happening is effectively a response to warming that's already occurred, and because the scenarios themselves don't diverge very quickly. But by the end of the century, the projections are substantially different. In RCP 8.5, we have 0.53 to 0.98 metres as our likely range by 2100. In RCP 2.6, only 0.28 to 0.61 metres. So it makes a big difference by the end of the 21st century, and also to the rate of rise. So the likely rate of rise in the last 20 years of this century under RCP 8.5 is between 8 to 16 millimetres a year, comparable to the rate of rise of sea level during deglaciation, so a very large rate. Whereas in R.6 it's much lower. But you observe that 2.6, you observe that the sea level has not levelled out in RCP 2.6 by any means. It's continuing at this rate, with not very much sign of reducing. The relationship between global mean sea level rise and CO2 emissions is not nice and simple, as in the case of temperature change, and I think this is something that should be borne in mind from a policy point of view. And that's because global mean sea level rise depends on the pathway of CO2 emissions, not only on the total emissions. And you can see that here. Well, so here I've plotted cumulative CO2 emissions against the global mean sea level rise by the end of the century. Clearly, scenarios with greater emissions in general have greater sea level rise, but you see that RCP 4.5 and RCP 6.0 have almost the same likely range of sea level rise, but their cumulative emissions are substantially different. And that's because they have different pathways. In RCP 4.5, the CO2 is emitted earlier, and earlier CO2 emissions cause more sea level rise because sea level rise is essentially proportional to the temperature change integral, time integral. So if you wish to mitigate sea level rise, the CO2 emissions have to be reduced earlier rather than later, and it's not just the total emissions that matters. Here are the projections of global mean sea level rise at the end of this century, decomposed into components for the 4 RCPs and also for scenario SRES A1B that was used in the AR4. This scenario wasn't run by the AR5 GCMs, but we are able to estimate its results quite accurately from other results that other scenarios that they did run. So the grey bars here show the sum and the likely range, and the coloured symbols are the components. In all scenarios, thermal expansion, glaciers, the Greenland ice sheet, the Antarctic ice sheet, and land water storage are positive contributions. For the ice sheets, we also have a bar, which is the contribution specifically from rapid change in ice sheet dynamics, increased ice outflow, that is. So you can see how much of that it is. In order to make a comparison with the AR4, which I think is a useful step, we have to somewhat reconfigure this diagram, as we had to approach this in a different way in the AR4. So I'm going to show you how the AR5 compares with the AR4 when we put it in similar terms for scenario A1B, which we have in both reports. So firstly, we rearrange the ice sheet terms. So now this is the Greenland surface mass balance contribution, so that's increased melting on the surface. And this is the Antarctic surface mass balance contribution, which is negative because of increased snowfall. And this purple bar here is the contribution from rapid increase in ice sheet outflow from both ice sheets put together, that purple bar. The AR4's projections were for the last decade of the 21st century compared with 1990, whereas the AR5's projections are for 2081, the last 20 years of this century, relative to 1986 to 2005. So they're not exactly the same. The AR4's end period was later, and its reference time was earlier. So both of those things take to make AR4 projections bigger. So if we re-express the AR5 projection with AR4 dates, it makes it bigger, like this. And then we can compare it with the AR4 projection for this scenario, which is this. So you can see it's quite a lot smaller. The largest reason why it's smaller is because this grey bar here includes the rapid ice sheet dynamics contribution, whereas the AR4 grey bar did not include the rapid ice sheet dynamics contribution. This purple bar here is the thing that was called the scaled up ice sheet discharge, which was included as an illustrative number. In fact, it's a number about the same size as we have in AR5, same order of magnitude. But because there wasn't a literature basis for this and very low confidence in it, it wasn't included in the projections. When people say that the AR4 projections were an underestimate, I regard this as a misrepresentation. Because the AR4 projections for SRES A1B, for example, were this range of numbers, plus a statement that we are not including rapid ice sheet dynamics, which is bound to make it bigger. And a lesson that we learned from the present reception of the AR4 is that it is very dangerous to give numbers with caveats, because people just ignore the caveats and misinterpret the numbers. And this is just a problem with communication, but it was an important lesson to learn. But that's the biggest reason, the biggest single reason why this grey bar is bigger than that one. But you see that the other terms are different too. The thermal expansion is about the same, but all the other ice sheet components, land ice components are more positive. And in addition, we have included this term here, the terrestrial, the land water storage term, in the AR5, which wasn't in the AR4, and that is due to that's an estimate of increased groundwater mining during the 21st century. So there are several reasons why the AR5 projections are larger. But the most important, as I said, is the rapid increase in ice sheet outflow. So a few words about what that is. What we have included, that is. So the general idea is what's going on, as Jonathan has also talked about, in the last couple of decades, is that warming of the ocean adjacent to ice sheets has led to warmer water under ice shelves, which is the part of the ice sheet that goes beyond the grounding line here, where it loses contact with the ground and bedrock. And so the ice shelf is actually floating, although attached to the ice sheet. So this causes melting under here. Warming causes increased melting under here, so the ice shelf gets thinner. And because the ice shelf is generally attached either to ice, adjacent ice, or is in an embayment, the ice shelf, in many cases, buttresses the ice sheet behind. So thinning of the ice shelf causes reduced buttressing and increased discharge of ice into the ocean. This is what's thought to have been happening, although we don't have very good observations of temperature changes in these regions, and we only have rudimentary models of the effect that would have. So our projections include this kind of effect becoming more intense in future, obtained, as I said, by a combination of process-based modelling and statistical extrapolation. But they do not include another possibility, which is known from theory and from modelling studies, that there could be an instability. The instability potentially occurs if one is in a situation like this, where the bedrock of the ice sheet goes downwards as one goes into the ice sheet. In these circumstances, it's possible, although not certain, that if the grounding line begins to retreat, it will then retreat unstably under its own dynamics, nothing to do with climate forcing. Now, there are some quantitative estimates of what this would contribute done on various different bases, and the numbers they give are not so consistent as for the more of the same, so to speak. But we think that it is only this effect, only the collapse of the marine base sectors of the Antarctic ice sheet, which is particularly prone to this phenomenon, which, if initiated, would cause global mean sea level rise that was substantially greater than the likely ranges. And we have medium confidence that this contribution wouldn't exceed more than several tenths of a metre. And the reason for not giving precise numbers here is because the literature doesn't really allow us to give precise numbers with the robustness that numbers would imply. Learning from the previous lesson, previous report, if we gave numbers, they would be taken to be very, very certain. Almost certainly, that's how people would interpret them. And whereas we understood that the order of magnitude is an important thing to convey, and that's what we intended to convey by this phrase, we do have confidence in the order of magnitude. Of course, that's not sufficient for planning purposes. If one is actually going to plan something that depends on having a number, then you have to choose a number. but that choice is going to be a bit arbitrary, and it's not something that we could derive from the scientific literature, so it's not the job of the IPCC to do that. It's the job of people who are going to produce planning guidance to do that. In the same way as you might design flood defences to cope with a 1 in 1,000 year event. That's an arbitrary choice. Why not 1 in 990 or 1 in 1,200? I mean, clearly it's just a round number. If you need a number for planning purposes, you have to make some additional choices. But we can't do that, we don't think, on the basis of the literature alone. That's why we stopped at that point. We are also asked, well, why can't we give the probability, why can't we say something about, in particular, the phrase usually used, an upper bound? Why do we only give a likely range? Why not an upper bound for sea level rise in the 21st century? Well, there are two kinds of reasons for that. One is that our projections are derived from climate projections, climate change projections, and they only give a likely range. So we can't define a very likely range or an upper bound if we only have climate input that claims to be a likely range. And the other and more important reason is that the literature doesn't allow us to do that with robustness. There isn't sufficient confidence to assess the probability of any specific level above the likely range, in our view. Obviously, one could say an upper bound for sea level rise in the 21st century is 100 metres, but clearly that's no use at all. If you're going to take a number that's in a range that's going to be useful, it's only going to be useful if you can give some indication about whether this is a 1% thing or a 0.1% or a 10%. And we don't think the science is able to allow us to attach probabilities like that to those numbers. One possible source of information is semi-empirical models. This is a model technique that was developed at the time of the AR4. The first publications were about the same time as the AR4, so they were not included in the AR4. The first paper was by Stefan Rahmstorff on this subject. He developed a correlation between the rate of global mean sea level rise and global mean temperature change in the 20th century. And then he used that to project 21st century sea level rise based on projections of 21st century global mean temperature change. And since then, Svetlana Yervieva and Aslek Grinstead and others have developed another model based on somewhat different principles, but with the same underlying idea. So these models are not process-based models, and they tend to give larger numbers, as I will show you in just a moment. This is a possible source of information about if you like, an upper bound. And we went through this in great detail. It was something we took extremely seriously. I'd like to thank Sveta for her contribution to that. And I think respect is due to you for sticking with it, because this is an important lesson that in the IPCC report, while it's often said in the media the IPCC is a consensus of what climate scientists think, that's not true necessarily. What the IPCC report is an assessment of the science. And it is possible in the assessment to say there is not a consensus. That all we have to agree on is our assessment of the science. We don't actually have to agree on the science itself. And indeed, we do have disagreements. We all have our own views, but we agree on the assessment in the end. Now, the interesting thing about the semi-empirical model projections is that they are, on the whole, larger. So here is a range of different semi-empirical models, compared with the likely range of AR5 for RCP 8.5. And in nearly every case, the 95 percentile, so these are 5 to 95% ranges, is higher than the process-based likely range. And the important question is, why is that? And of course, the semi-empirical models themselves can't tell us, because all they're telling us about is the total sea level rise. But nonetheless, we have to ask why that is. A reason that has been suggested in various places is that it's because, and this was indeed one of the motivations for developing these models, because these models include rapid ice sheet dynamics, whereas the process-based models don't. Implicitly, of course, not explicitly. But we don't think in the end that there is any evidence that this is the case. And that's because the rapid ice sheet dynamical change isn't a very large contribution to 20th century sea level rise. You see, you can largely explain 20th century sea level rise with thermal expansion and glaciers. If it's the case that, we don't know, of course, as Jonathan has said, what happened exactly before 1990, but if this acceleration of ice sheet outflow is a recent phenomenon, then it's only contributed 14 millimetres to 20th century sea level rise, not a large term. Now, the semi-empirical model will only relate that to global mean temperature change, and if it's a small fraction in the past, it can't be a large fraction in the future, capable of explaining why the projections are up to twice as big. So that's one reason. And the other reason is that we don't have any direct evidence, we don't really have any evidence that the temperature changes that may be forcing ice sheet dynamical change are related to global temperature change or radiative forcing. So they may not actually relate to the temperature change scenarios. So because of these kinds of considerations, there isn't agreement in the scientific community about whether this approach is reliable. Of course, some people think it is, other people think it isn't. And because we haven't got a consistent explanation of what's going on, that is, we can't square the model results with other evidence about the physical components, in the end we reach the assessment that we have low confidence in these projections. And that's why the likely ranges are based on the process-based models, and there isn't an upper bound derived from semi-empirical models. But I went through this in some detail to make clear that this wasn't a light decision. It was a very difficult debate where we're trying to do what we are charged to do, which is to give the government's policy-relevant understanding of what the science says. So then, turning finally to the longer term, it's virtually certain that global mean sea level rise will continue for many centuries beyond 2100. And you can see that was the case from the previous time series, where, as I pointed out, even in RCP 2.6, the lowest scenario, sea level was continuing to rise at 2 to 7 millimetres a year at the end of this century. But the amount of rise will be strongly dependent on future emissions. It will diverge even more as one goes into the further future. And we have here some estimates for low and high CO2 concentrations at 2300. These are not expressed in terms of RCPs because the RCPs themselves only go up to 2100, and some of the most of the model evidence on which these statements are based come from model experiments with idealized CO2 scenarios. Larger sea level rise on the long term could result from sustained mass loss by the ice sheets. So on the long term, it's much more likely, indeed, maybe even certain if one goes further into the future, that you would get a marine ice sheet instability, and you would lose a substantial amount of ice from the Antarctic ice sheet. And some part of the mass loss from the ice sheets might well be irreversible, meaning even if the climate subsequently reverted to pre-industrial, the ice sheets wouldn't necessarily regrow. This graph here shows one model study of total sea level rise in equilibrium as a function of equilibrium global mean temperature change. So this is after a long time, long enough for the ice sheets to come to equilibrium. And you see that this model generally expects that for temperature change here and here in these ranges, global mean equilibrium, global mean sea level rise is about 2 more meters of sea level rise for each additional degree of global mean warming. And the shape of this graph is being compared here with these uncertainty ranges in both temperature and sea level for the Pliocene, for the last interglacial, and for a previous interglacial, being isotope stage 11. So they're roughly consistent. Of course, there are large uncertainties on the proxy data. And then you see there's this step here. This feature is associated with the Greenland ice sheet, and with our belief, with high confidence on the basis of quite a lot of modelling results, that there is some threshold of warming beyond which the Greenland ice sheet is not viable anymore. So if you exceed that temperature and you maintain it indefinitely, the equilibrium situation would be that the ice sheet would virtually be eliminated. But there is uncertainty about what the threshold actually is. And there's a range of model results. Taking current literature, we believe that the threshold is greater than 1 degree, but we only have low confidence in that because there is really only one model result that suggests another part of the range. And there are several results that suggest that it is less than 4 degrees with medium confidence of global mean warming with respect to pre-industrial. So clearly, because this threshold is quite an important one, for example, if we were thinking of temperature target warming of 2 degrees, you would like to know, is that below or above the Greenland viability threshold? Because if 2 degrees is more than the threshold, that means that 2 degree target eventually commits you to 7 metres of sea level rise on a long time scale. The time scale is indeed centuries to millennia, and it could be irreversible either wholly or partly. And one other piece of evidence that ice sheets do indeed respond more with large sea level rise to elevated temperature if you maintain it for a long time comes from the last interglacial, where there are a number of pieces of proxy evidence that suggest that for several thousand years, global mean sea level rise was at least 5 metres higher than present. This shows some information from Australia. Of course, this doesn't appear to go up to 5 metres of sea level rise, but this isn't an estimate of global mean sea level rise, it has to be adjusted. Putting various proxy informations together, you get the impression that there was a period during the last interglacial when sea level rise was considerably higher than now, and during that period, high latitude temperatures were warmer than now, maybe up to 2 degrees or so. It's not a direct analogue, however, because that warming was orbitally forced. It wasn't caused by higher CO2, which was rather like now. It was because insulation was different during the last interglacial. That's led to the warmer high latitude climates. So the Greenland ice sheet very likely contributed from modelling results and some proxy data and some evidence from the ice sheet itself between 1.4 and 4.3 metres. So if it was at least 5 metres, that means there, with medium confidence, must have been a contribution from the Antarctic ice sheet as well during the last interglacial. The Antarctic ice sheet must have had less mass than now. Okay, so I'm not going to say much about this because I'm almost out of time. But tomorrow, Caroline Katzmann is going to talk about regional sea level projections. So I will just give the headline statements that are in the SPM. It's very likely that sea level will rise in the global mean, but in more than 95% of the ocean area. And that comes from taking into account the effects of ocean circulation and dynamics, the effect on the geoid of redistribution of mass, and the effect of glacio-isostatic adjustment. The blue areas on this graph where sea level does not rise are areas that are strongly affected by post-glacial rebound. So that's not the result of 21st century climate change. And about 70% of the coastlines worldwide are projected to experience sea level change within 20% of the global mean. And that's what these histograms indicate for RCP 4.5 and RCP 8.5. So global mean sea level rise is a fairly good indication of local mean sea level change. And because of mean sea level rise, it is very likely there will be a significant increase in the occurrence of future sea level extremes. And this map here shows what happens to the frequency of extreme events derived from extreme value, fitting an extreme value distribution. If you have a local sea level rise of 0.5 metre, and the size of the symbols indicates by how much more likely a given extreme becomes, and they range. These are tide gauge sites. That's why they are where they are. In many places, 100 or 1,000 times more likely for a given extreme sea level rise. So to summarise, global mean sea level rise during the 20th century can be accounted for by ocean thermal expansion, ice loss by glaciers and ice sheets, changes in liquid water and storage on land, and the 20th century as a whole, the thermal expansion and the glaciers are the dominant terms. It's very likely that the 21st century rate of sea level rise will exceed that which has been observed in the last few decades, and it will be due to the same processes. We have derived likely ranges for global mean sea level rise for the end of the century, which depend on the emission scenarios, and we have medium confidence in these likely ranges, which include the contributions from possible changes in rapid ice sheet dynamics. But this isn't necessarily all. If there is in fact a marine ice sheet instability which begins during the 21st century, it would add more to these totals by several tenths of a metre during the century. It's very likely that sea level will rise in most of the ocean area. It's very likely that that will lead to a significant increase in the occurrence of future sea level extremes. And it's virtually certain that sea level rise will continue for many centuries beyond this century, and the amount of rise will depend on emissions during this century. The end.